A few years ago, these are my watercolor paintings, and it took me many years to even get to this point, but I really wanted to learn, and it's nice to be an artist and find a creative outlet. And now, if I were to upload, so I improved, as you can see, that's me, AA on the left, improved a little bit, but you see AI on the right can actually take my images and create something similar, maybe even better, and it's both shocking and fascinating at the same time, annoying too. Like I can imagine what creative industries people think about this. And as an artist and as a scientist, I had mixed feelings about this technology. Let's just say that. So a very brief history, and I think we should have connected the dots from when the term AI was coined by John McCarthy to Turing's paper, and that would have been interesting, like you said. But yeah, so it has a good almost 6-7 decades now when this term was coined. And over the years, as you said, we've had many AI winters and summers and different types of AI. What we're seeing right now with foundation models or generative AI or frontier models is one type of AI, right? We've had different AI systems in the past. And so IBM's Deep Blue, when it defeated the chess champion in 1997, that was a big AI moment, followed by, again, IBM's Watson winning in Jeopardy in 2011. And then in 2016, we had Google's AlphaGo beating another world champion at the game of Go. And you can see a pattern here that every time we're talking about an AI milestone, it's in comparison to an expert and a human expert in a given field. So, and that continues even today, where every time we say LLMs have reached a critical milestone, we're always comparing them to human intelligence on a given task, right? So the human intelligence remains a benchmark for how we measure AI performance. And so in 2020, late 22, when OpenAI released ChatGPT, it was again in that same vein, like human-like language processing. So here is a task, a natural language processing task. This is how humans perform on it. This is how ChatGPT performs in it, and how far are we or how close are we, right? And over time, the models keep getting better, and so we have to keep creating newer and more challenging benchmarks, right? And there's a whole issue of data contamination, whether these models already have seen the test set somehow in their training data, like that's a whole different area. And so early this year, we were hearing the term AGI quite a bit, artificial general intelligence, superintelligence. Have you noticed that in the last 1 or 2 months, we've actually stopped hearing a lot about AGI, or if that's just my impression, right? So that also tells you, like, a lot of these terms are, as you pointed out, marketing terms, right? So at some point, how do you define the next big breakthrough? Well, let's call it AGI. Can anybody define what AGI is? I don't think so. I don't know. And then there's another thing that you can notice here is the divide between the businesses, the big tech that are actually developing these very large models and the fancy terms that they use versus the research community. So I don't come across many papers in my own field saying, this is an AGI model, right? Or anything like that. Like, we don't even talk about like AI model. It's still a very specific form of AI that people work on. It is ubiquitous. We are using it in almost every application that we can sort of, and apparently if you have AI native products somehow, that's even a bigger buzzword, and people are really interested in funding that, for instance, right? So language models in the real world, in all of our research work, in our community, they are basically part of everything that we do now. And the number of papers that talk about large language models right now is in tens of thousands. In fact, one of the biggest AI conferences called AAAI, if some of you are familiar with it, it received 29,000 submissions this cycle 2 months ago, right? So that's a lot of AI research in a single conference. And then you have similar ones in others. So needless to say, research world is crazy about AI right now, as is industry, right? And so we have all of the big tech investing heavily in this technology. You might have seen some of those news headlines and talent wars and whatnot. And my question is, our lab continuously keeps thinking, how does it really affect us, right? So I wanted to show something interesting. So this, I would say, is from maybe 3 or 4 months ago. There are several of these benchmark leaderboards, and this one is called LiveBench. There's a couple of others, LLM Arena. And what they're doing is trying to have a more contamination-free way of benchmarking LLMs. So, right, there are those standard benchmarks that are already out there. And these people have created benchmarks that they withhold and don't release out into the public. And then they benchmark. So this is supposed to give you a more realistic picture of the performance. And if you see the columns up there, they have different tasks. So there's the global average, but then you can break it up into reasoning tasks or coding tasks or data analysis, math, right, and so on. And a few months ago, that was the ranking. So you had Google's Gemini 2.5 Pro being at the top, and followed by Anthropic, and then you had OpenAI's models O3 and O1 and so on. The ranking has shifted. So GPT-5 from OpenAI, in fact, the top 5 are now going to OpenAI, right? Followed by Anthropic, and then OpenAI. So Gemini has fallen further down in this leaderboard. And so it keeps changing. And then the other interesting thing is they've included a new task called agentic coding, which wasn't there 3 or 4 months ago. So new, as I was telling you, new benchmarks, new tasks keep getting added, and this is continuously in a flux. Very brief history of LLMs. So we had statistical language models in the 1990s, and neural language models started seeing a little bit of an uptick in early 2000s, but it wasn't until 2013 when we had the first neural models called word-to-vec embeddings. And at the same time, we had GloVe and a couple of others. These were very specific, worked at word-level embeddings. And so I joined the field around, I would say, 2012, so right before word-to-vec came onto the scene. And then the next big was like we were using different types of neural architectures here. And so this is what I want to point out. What we are currently using was not the original architecture. It took time before we settled on what we are using in current language models. So we were using recurrent neural networks, LSTMs, feed-forward networks here, and then attention mechanism was introduced in around 2015 for machine translation, right? And then the big breakthrough came in 2017, when we combined the feed-forward neural network with the attention mechanism to have a new transformer architecture. And that was, needless to say, the biggest shift in this area. So using transformer architecture now, 2018 was a very interesting period. We could have transformer encoder models like BERT, or we could have transformer decoder models like GPT. And they are built a little bit differently, and they are better in different tasks. So for instance, BERT was better in understanding tasks, and GPT was better in generating tasks. And at that time, Google's BERT model was considered to be more superior. It was doing much better on a lot of benchmarks, right? And GPT was okay, but it could generate text, but not really answer questions with any precision. And then somehow, now don't ask me to explain what happened to the BERT, Roberta series of models, but see, Google seems to have lost something here because OpenAI continued focusing on their GPT architecture and kept scaling it. So there came GPT-2, then came GPT-3, and then the biggest one in 2022 was ChatGPT, which was a conversational model built on top of a GPT model. And this is around the time in 2020 or so, we started calling them large language models. So we've had the name change. Like we used to call them neural language models, or statistical language models, then pre-trained language models, to now like large language models. And now we have multimodal models, which can not only process text, but also images and videos and others, right? So yeah, just wanted to give you a little bit of an overview that we could have gone in a different direction, right? Had Google kept investing in scaling BERT type models, we would not be in generative AI era, we would have been a discriminative AI era, which was a different type of training. But anyway, it's interesting to see how we didn't just land here in one shot. It was a couple of pivots, and I think a lot of luck too. Okay, so very, very briefly, I won't bore you too much with this, but I wanted you to give you an intuition of just language model. So if you think about them, there's the sequence of words, the mouse ate the cheese. The probability of this particular sequence of words appearing in a very, very, very large corpus of text, so think billions of books and web pages, let's say 0.02. I'm just making up a number, right? But then, if you were to, if I were to ask you to put a probability to the cheese ate the mouse, what would you say? It's hard to guess, but something smaller than 0.02, because you understand that that's a little bit less common. And then if we were to say mouse, the cheese ate, maybe even smaller probability, right? So that's the intuition behind language models and how they're computing the probability of sequences of words and how they can appear in our text, in our language, right? And you can do this across multiple languages. These are made up numbers, by the way. Okay, so if you think about it, it is quite a simple method. But the simplicity is deceiving because we had to use our implicit world knowledge to say, mouse the cheese ate is very low because it's ungrammatical, or the cheese ate the mouse is less likely because of world knowledge, right? So we're using a lot of implicit knowledge to figure out how language is structured. Right? But models have to learn this from data because we're not hard coding any linguistic rules here. And that is why these probabilities only really become useful at scale. They really need to see lots and lots of data. And so until 2018, 2020 even, we had all of these language models in research labs all around the world. Everybody was able to work on them. On their GPUs, it wasn't that expensive, but they weren't ready for the real world because they were small, they hadn't developed that, When we scaled them up, when we just kept training them, they got better. So scale was one of the biggest breakthroughs. So if you see the size of these circles, so each of these circles are different. Think about LMs, and the bigger the size, the more parameters, the bigger the model is. And on the y-axis, what you have is their accuracy, their performance on a task called MMLU, which is a question answering task. And you can see on the x-axis, you have the years, the range, going from 2022 to 2012, and we're seeing that they generally keep improving. And this is where you see this dotted line is the human expert line, 89.8, right? So somewhere there, and at some point you're seeing models starting to surpass the human performance on MMLU, right? So that's one indicator that models are doing better. I just quickly want to walk through some main steps, and this is a highly oversimplified version of how these models are trained, but it really all starts with lots and lots of data. And so, they've scraped a lot of data, gotten into trouble with copyright and everything else, found a way to, ask for forgiveness and, fix all of that stuff. Like recently, I think Anthropic settled a big copyright case with artists, which I think per artist, I think it comes down to $3,000 or something of that sort, even though the bigger, larger number is in billions of something. But anyway, first thing was scrape everything that we can get our hands on. So in the very beginning, GPT-2 models were very small because the developers were being very careful where can they get the data from? Like, well, what is publicly available and what can we actually, so Wikipedia was game for everybody, right? So that was the first go-to. But over time, as their need increased for larger data sets, they just started scraping everything. Recently, I read about Claude models will also start using your chat transcript unless you opt out or something. Or so for people who use those models, you will start seeing those notifications. They want to use your data, but this one is asking for permission, at least for now, right? Okay, then this is the architecture I was talking about. So we're talking about this is the transformer model, but again, the combination, the secret was really the feed-forward model with the attention mechanism that really made it easier to train, first of all, compared to the RNNs and the other LSTM methods or architectures before, but also made them better, right? So just in general, even though at this point, there may be better architectures out there, proven by research, somebody needs to scale them to actually bring them to practice, right? So there's lots of modified versions of this right now. A lot of the details we don't know because they're proprietary. And now we have lots of data and you have this neural network. What do you actually train it for? You train it for predicting the next word. It's as simple as that. Here is a sequence of text. What is the next most likely token? Okay? And I should also clarify, they don't really work at the word level. They work on something called a sub-word level. So it's somewhere between a word and a character, right? But that's just for easier training. And so if you say the students open there, and then the model will have a probability distribution across all of the words that are possible in the vocabulary. And so let's say books gets some probability followed by laptops and so on, okay? And so at this point, the model may guess books, right? It may predict books. But you actually go back and say, no, according to my data, it should be they opened their laptops, right? And so you will compute the distance between books and laptops, and you try and so make that loss smaller. So then you send that back to the model as a signal, and the training continues. So you do this over billions of sequences, and you keep asking the model to predict the next word, and over time, its predictions get better and better and match what you were looking for. So now we've taught the model how to predict the next word. And so let's say we say, explain the moon landing to a 6-year-old in a few sentences, okay? And what does the model do? It continues to predict the next word. So it continues to say, explain the theory of gravity to a 6-year-old, or it might say, explain evolution to a 6-year-old, but that's not quite what you really want. You want the answer to the moon landing question that you posed. So how do you go from predicting the next word to actually following your instructions? Okay? So here, this was not possible using existing raw data that you scraped willy-nilly from the web, right? Now you have to create your data. Call it instruction following data, task instruction, something. Here you show the model examples of this is a prompt, this is an expected response. And this is one of the secret sauces, because it's very expensive to have humans help you create this data, okay? But when you create that data set and you train that same model on it again, now when you ask the question, it can actually give you the answer. People went to the moon, took pictures, da-da-da-da-da. So this is when we taught models to start following our instructions. Next thing is, well, sure, you can follow my instructions, but you may give me something offensive, harmful, right? I now teach you how to follow my preferences. So you generate some pieces of text, and I say, well, this one is nice, and this one is not acceptable. And then I give you that signal again. Where do those signals come from? Humans again. Humans help prepare this sort of data at scale, mostly in developing countries, crowdsourced workers, and then you teach the model again. So this is yet another post-training steps. And right now, we're in this era where we're continuously aligning these models to our preferences, to our values, different ways of alignment, and several post-training steps continue. The most recent one is, well, start to reason a little bit. So instead of directly jumping to the answer, first generate a reasoning trace and then come to an answer. Okay, so when I ask you a question, now the model is trained to, let's break it down step by step, something. Okay, so now we added reasoning on top of it. So basically I'm telling you, like, the current version of generative AI models have undergone a lot of post-training steps, and these things are still being figured out. Right now, like, agentic AI is a big deal. We'll stitch. If one LLM cannot get us there, then let's have multiple LLMs be more specific and specialized and help us get there. Okay, this was, just wanted to point out, just about two and a half years ago, there was a big, push towards pausing all AI letters. Lots and lots of people, including top computer scientists, signed it. You will see interesting names in here, Anyway, nothing came out of it, is what I have to tell you. We just continued going. Jeffrey Hinton, he's one of the people responsible for the early development of neural networks that we use, has been issuing a lot of cautious warnings about this technology. But at the same time, we have people like Eric Schmidt, who says the AI revolution is underhyped. We need lots more data centers. We need, to have AI for science and those sort of things. So I just wanted to sort of say that this is a confusing time. There's a lot of debate going on whether this technology is good for us or, perilous for us, or is there something in between that we can find good uses of? Yeah, so this was interesting. This was in May. In the court of law, some lawyer's firm, came up with some argument, and the judge found something misleading in that, and they asked for more details, and then they came up with a new brief that had even more mistakes in it, and then when they asked the attorney to give sworn testimonies to explain the mistakes, they said, well, they used Google Gemini as well as law-specific AI models to write the document, and it ended up having, we famously know these things as hallucinations, but basically inaccuracies, false information, right? So talking about that, technology that is still under development, right? If you ask any of the researchers, have we really created a very powerful AI model? I don't think anyone would say yes, because we spend our time looking for mistakes, and we can easily find them. But also, at the same time, this technology is being used in real world, many applications. So this is a very interesting study that just came out, and it said what large language models know and what people think they know, okay? So here is a question, multiple choice, and here's a short answer question, and the model chooses between A, B, and C, and D, and says, okay, 0.46, the answer is C, okay? And looking at this model explanation, the human has a 95% confidence that the model's answer is right, okay? And similarly, for a short answer question, it says, I'm not entirely sure, da-da-da-da-da, and so the model, even based on this, humans say, okay, model is less confident and maybe wrong. The funny thing is both of these answers are wrong, right? The model didn't get it right in either of these cases. Here, I believe it was A or something, and here the answer was the bluebird or something, right? But we tend to believe if the model is telling us that it's confident, we believe its confidence levels. And then there was this lot of good research coming out of Anthropic. They published this saying reasoning models don't always say what they think, and there's a very interesting paper, we can talk about it later. And so they looked at the reasoning traces of their models and found that the reasoning does not match the model's actual reasoning or the output, right? So there's a disconnect there, and we cannot really just always believe what the model is telling us. On the other hand, this is from IBM, I think earlier this week. It says AI starts to explain how, something in the drug discovery labs. They've developed a special protein language model, and they're actually looking under the hood, and they are able to find interpretability studies, to find actual layers of the model that are responsible for the prediction, and that actually helps the users trust the model more. And in this case, they're finding that there is an actually nice connection between the prediction and the interpretability. So again, good and bad, right? It maybe depends on the task, maybe depends on the model when that aligns. This is from our own lab, one of our students, Sina. He asked Google, where is ACL 2026 happening? This is one of our top conferences in our field, and he's eager to submit a paper. And then very confidently, AI Overview tells us that it will be happening in Brazil, right? And you would take that and say, okay, everything looks right. The name is right, Association for Computational Linguistics, yes. Actually, it's happening in San Diego, right? And so the AI Overview was wrong. This was a couple of weeks ago, but still, right? And so a lot of us just looking at AI Overview. And so yeah, this is an active and interesting space to be in. Thank you.